Where do we leave off? We're going to quickly do lecture 16 and jump to lecture 17. Lecture 16 introduces series. What is a series? Yeah, it's a summation of a sequence, exactly. So the definitions, if you want to look at these new definitions, a series is just a new sequence whose elements are the partial sums of the original sequence. Okay, so when we say a series, so that's what it means to be a series. A series is just a sequence of partial sums. So you give me a series, A, from the naturals to the reals. I'll give you another series from the naturals to the reals, which is the sum over k up to n minus 1 of ak. Then what does it mean for a series to have a limit? For a series to converge to a value? Exactly. The sequence of partial sums converges to that value. There's nothing new happening here. Okay, seek lim. It's the same definition as before. It's not a new definition. The only new definition is series. Series is the sequence of partial sums, and then that sequence of partial sums converges to L. Or if I don't want to say what that L is, I'll just say the series converges. A series converges if there exists an L. All right. So let's prove our first exercise. Let me pull this all the way over. Let me pull this all the way over. Our first exercise is that in order, a necessary condition. So theorem. Let me go over here. There we go. So theorem. If a series AN converges, this is how we write a series converges. I don't know why that's how we write. I do know why that's how we write a series converges. Maybe I'll just say it in words. Converges, then a necessary condition for that is for the terms themselves to go to 0. So we have the assumption HA that the series converges, and we want to prove that the sequence of the A's goes to 0. Okay, so we'll call this HA, and then this is our goal. How can we do it? Joe?
You start proof by contradiction and get some epsilon for.
You can do it by contradiction. You can. Yeah, let's talk about approach one. Approach one. Let's just do sketches first. Sketches of proofs. Sketches. Approach one. If not, then for any epsilon, there exists an n such that an is at least epsilon. All right. No matter how small an epsilon is, you can go far enough out and you'll find, let's see, I want to say something more than that. For any epsilon and for all n, there exists an n greater than n, so that you can find a term that's more than epsilon.
Okay.
I'm sorry. Thank you. So give me, if not, then there's some epsilon, so that no matter how far out you go, there are terms that are of size at least epsilon. Well, then what's wrong with that? What's wrong with the partial sums converging? Jeffrey.
Basically, you're going to always add enough epsilons to like exceed.
I can't conclude that I'm going to be going off to infinity, which is why I don't like the less than infinity symbol for convergence. Unless you put absolute values on the series. It might be bouncing around. Like the sequence -1 to the n. The series of that, well, it can't converge by this theorem, but why not? Suhas.
You could just like use epsilon over 2 and then like like at most it's going to be like epsilon 0, right? At most you can like by triangle inequality you could stack 2 on top of each other.
Well, I think I see what you're trying to do. The problem is, who do I stack it on top of? The keel. Okay. Okay. What I'm trying to get you to say, so this is all closely related actually to approach two. What I'm trying to get you to say is that if you look at if the sums are converging, then they're going to get very close to L. And if the partial sum before you reach N is within epsilon over 2, maybe that's what you were trying to get at, that you would hang your hat on L, because we know that the sequence converges, so it converges to L. So if this sum is L, converges to some limit L, then this difference is less than epsilon over 2. But then when I add one more term, the next term, but when I add one more term, this should be a k or something, k going from 0 to n minus 1. Now, if I add one more term, k goes from 0 to n minus L. This must also be less than epsilon over 2, but that's not possible. Okay, so approach one is to do it by contradiction, but there's no reason to do it by contradiction. Let's do it directly. What do we know about, so sketch of direct proof. The point is this sequence and this term in the sequence of partial sums and this term in the sequence of partial sums will differ by too much. How can we compare different terms in the same sequence? Yes, what property thinks about that? Joe? Yes? The Cauchy. Yes, exactly. Because, so, what is it called? We know that if a sequence converges, then it's Cauchy. So HA implies the sequence of partial sums called series A is Cauchy. And Cauchy says, i.e., for all epsilon, there exists an n, so that for all n, at least n, and for all m, at least n, the partial sums up to m of ak minus the series up to n of ak is less than epsilon. And what's wrong with that if there's a large value? How do I capture there being a large value? What's the idea? How do I isolate a single value of A? Akil? Bingo. Okay, there's a very, very simple way to do it. You just said, so this is what we know, this is what we know, and now apply to m equals n plus 1. If I said m equals n plus 1, then this difference is just an. Well, if an is less than epsilon, well, that's exactly what it means for an to be going to 0. Okay? Does that make sense? So we're going to use the Cauchy property of limits, and that'll be a nicer proof than having to go between this and L and fighting with epsilon over 2s. We can just go directly there. The Cauchy property already did the epsilon over 2s for us. It's more powerful in this, in general, but in particular in this example. Okay, does that make sense? So let's try to write out now a formal proof. Okay, proof, proper proof. All right, so we're going to prove that the sequence of the A's converges to 0. Akil? So this is really the sum up to m minus 1, and this is the sum up to n minus 1. Yeah, thanks. I'm being a little sloppy with my indices, which of course Lean will not allow me to be. Yeah, good question. Other questions? Make sense? Let's do it. Okay, so seq_lin means for any epsilon there exists an n. Okay, so given epsilon, so intro epsilon, H epsilon. We know that epsilon's positive. We know the sequence converges. What is that called? It's probably called is Cauchy of seq lim or something. Or seq conv theorems. Is Cauchy of lim. Okay, is Cauchy of lim is a bad name for this theorem, actually, because it's not about the limit, it's about the convergence. It should be called is Cauchy of seq conv. Maybe I'll remind myself later to change it. Is Cauchy of seq conv. That would be a better name for it. Okay. So it's called is Cauchy of lim, sorry. That's just too bad. Slide. Okay. So is Cauchy of lim, and then I need the fact that something converges. What converges? The series of A. So HA, I think it should be able to see through that. And that'll tell us that the sequence is Cauchy. What value of epsilon do we want to stick into it? The same epsilon. We don't have to do any epsilon over 2 stuff. So you stick in the same epsilon, and the fact that that epsilon is positive, that'll give us an n. So let's choose NHN using this. And then use that same n, use n, intro NHN, because we're trying to prove AN minus 0 is less than epsilon. And now if I were to specialize, so now I can just specialize HN to what value of little n? That little n. How do I know that little n is greater than capital N? HN. What value of little m? N plus 1. And why is that greater than n? Bound, okay, by bound. So now we will have the fact that, what will we have here? What will HN now look like? Let me put it here.
The absolute value, the sum of A.
Exactly. It'll say series A n plus 1 minus series A n in absolute value is less than epsilon. Okay, does that make sense? Now we want to get out of the series. So let's change this to, we're going to change at HN to what? A sum k in range n plus 1 of AK minus a sum k in range n of AK. Absolute value is less than epsilon. And now what do I want to do? Yes, how do I get this? What's the, why is this difference? Why is this difference when m is equal to n plus 1? Why is this difference just an? Jeffrey?
I forget what the theorem is called, but it's the thing that says that you could basically take out the, like separate the last term.
Yes, it's like the sum with a successor. It should be something like some successor. Let's see. We're on theorems, and it's going to be sum range suc. Okay, the sum range successor, sum over a range. So let's rewrite. And what do we want to show? We want to replace sum of k in range n plus 1 AK with what? And by apply, before I forget the name, sum range successor. Okay, what's it going to turn that into? Sum over k in range n, AK, plus the last term, an. Okay, so we can write that, rewrite that at HN. Rewrite this at HN. Once we've rewritten that at HN, now what? Now what can we do? Yeah, let's change this by ring. So, well, I guess I'll just say, again, rewrite and show the sum up to n of AK plus an minus the sum up to n of AK equals just an, and this is by ring. We'll rewrite that at HN. Does that make sense? And now HN just says the absolute value of AN is less than epsilon. But what's the goal? So after we at this point, the goal says yes is less than epsilon. So we're almost there. We just need to do a little ring on this. So rewrite show AN minus 0 is equal to AN by ring. That's at the goal, so I don't have to say anything, and then just apply HN. That make sense? Pretty simple. So the core idea, I hope, is clear. You set m equal to n plus 1. This difference is just AN itself, and then that's less than epsilon. Let's do it. So the proof is right here. Intro epsilon h epsilon. Intro epsilon h epsilon. Beautiful. Now choose NHN using is Cauchy of lim HA epsilon H epsilon. We're throwing an awful lot into that line, but I think it's good. Nope. Okay, so it doesn't see through seek conv. It doesn't see through seek conv. Okay, so the reason it doesn't see through seek conv is because we have to remind it what it means. So let's change. What is this? Seek conv series A at HA. It couldn't see through the definition, unfortunately. Now let's try writing all that again. Choose NHN using is Cauchy of lim. Now HA should work with epsilon H epsilon. Still no. HA has type C. Oh, I have to say what the sequence is. Is Cauchy of lim. So it might have worked. It might have worked. I just forgot to say what the sequence is. So this is an instance where curly brackets would be much better. If we had curly brackets on the sequence, you wouldn't have to specify the sequence once and then a second time specify that that sequence converges. You can figure out what the sequence is from the fact that it converges. So I'll add a curly bracket for the A for seek conv, and that'll make our lives better. Let's see. Does it take it now? Now it takes it. And it probably would have taken it the previous version too without needing to change the HA. Okay, sorry about that. All right. So that gives us a capital N. Let's use that capital N. And intro NHN. Beautiful. And I don't know, should I just ring normal form at the goal just to make our lives a little bit better? There we go. I cheated a little bit. I used the naked tactic. I told you not to use naked tactics. But we all know what it did. Okay. This series AM, I wonder if it'll see through the definitions without the change. Should we try? Let's first specialize HN to our little n, the fact that it's bounded. What value of little m? This is the only idea in this entire proof. M plus 1. And by bound. Great. And now let's do another naked rewrite. Sum range suck. Sum range suck at HN. It didn't do it. All right. So I didn't think it would see through the definitions. Ideally it would, but it doesn't. Okay, so let's change at HN. And what are we changing it to? Absolute value of sum. What happened? Something is less than epsilon. And what is that something? It's a difference of two sums. The first sum is k in range n, a k, not n, but n plus 1, because that was the value of m. Am I going too fast? K in range n of AK. Good. Now can we rewrite? Oh, did I say rewrite without saying where? No, I think I did say where. Sum range suck at HN, please. Okay, again, I'm doing naked tactics because I want to move things along. Ring ring, normal form at Hn. Beautiful, and apply Hn. Okay, so pedantic stuff aside, I saved us a lot of characters, but I hope you're happy with the proof. Any questions? Okay, that was level 16. Let's move on to level 17. So level 17. Let's start with the Leibniz series. Okay, let me slide this over. This is a series. Leibniz was far from the first person to make this observation, but for some reason, his name got attached to it, at least in some circles. So here's our sequence. An is equal to 1 over, I'm just reading from right here, n plus 1 times n plus 2. And let's just play with that a little bit. So what is the sequence? What is the value when n is equal to 1? When n is equal to 0. Yeah, I'm still not used to starting at 0. Yeah, when it's 0, we get a half, and then a 6. So this was 1 times 2. This is 2 times 3. 3 times 4 is 12th. 4 times 5 is 20th. 5 times 6 is a 30th, and so on. Okay, that's our sequence. What does that sequence add up to? So that's the problem. Summation an. So how do you deal with such a thing? If I gave you this right now as a midterm, what would you do? Panic? Pull out a calculator. Well, maybe, okay, so what would you compute with that calculator? Let's compute partial sums. Yeah, let's compute partial sums of the AKs, okay? So these are the ANs themselves. Here are the partial sums. So the first partial sum when n equals 0 is a half. What's the next one? A half plus a sixth. 2/3. Okay, 2/3 plus a 12th. 3/4. 3/4 plus a 20th. Okay, 4/5 plus a 30th. 5/6. Okay, all right. So I think we're getting the pattern here. So this would not be so difficult. You just start playing with the partial sums and you immediately see what's going on. So what is our claim is that if Bn is the sequence of partial sums, then what's a formula for Bn? I think it's n plus 2. When n is equal to 0, yeah, n plus 2. Okay, that's a 2. That's an attempt at turning a 1 into a 2. Is
1 minus.
1, that's a 1 minus, sorry. 1 minus 1. Okay. Can we prove this? So this is our claim, that the Bn's actually are equal to 1 minus that. How would you prove such a thing? Suhas, you got an idea? Algebra, okay. Algebra will only get us so far. We'll definitely use algebra, but
I mean, like, right, AN is like
very good. So the ANs you can write as 1 over n plus 1 minus 1 over n plus 2. I like that. Oh, so just multiply this out and you cross multiply. This is n plus 2 over n plus 1 times n plus 2. And this is n plus 1 over n plus 1 times n plus 2. So they just cancel and you get a 1 over n plus 1 times n plus 2. Jeffrey?
Get the expression for and keep this.
That's the keyword. Okay, to prove things like this, we need to use induction. Okay, no problem. So induction. So when n is equal to 0, B0 is equal to A0. And A0 is equal to a half, and a half is equal to 1 minus 1 over 0 plus 2. Okay, great. So now we assume the induction hypothesis that Bn is equal to 1 minus 1 over 2 n plus 2. And our goal is to show that Bn plus 1 is equal to 1 minus 1 over n plus 1 plus 2. This is a good quiz.
So like just the.
Yeah. Yeah, we already did the n equals 0. How do you do this part? Again, talk to your neighbor if you want to. Should I scroll up so you can see what an was? How are you guys doing it? What's the first step? Other than Jeffrey, other than Suhas?
We're assuming that the n is already equal to 1 minus 1 over n plus 2.
Correct.
So it's kind of like you're tacking on one more term.
You're tacking on one more term. Exactly right. That's it. That's all of induction is series. You tack on one more term. What do you know about Bn? Bn is a sum from 0. Bn plus 1 is a sum from 0 up to n. And Bn is a sum from 0 up to n minus 1. So B0 is a sum. Sorry. So B0, so B0 should be, this should be an n plus 1. B0 should be 0. An empty sum.
So.
Yeah. So B0 is 0. We're going to see the algebra either work out or not. We're going to find out in a second. But this should be the way that the series is set up is that the nth term of a series plus the nth term of the sequence is the n plus first term of the series. So hopefully the algebra works out if we get the answer right.
So wait, B of n is 1 minus 1 over n plus 1.
I guess so, yeah.
Okay.
Yep. So then B of 0 should be 0, which matches because it's 1 minus 1 over 1 plus 0 plus 1. There we go, which is 0. A starts with a half. No, B0. So remember, the sum of k in range n is a sum from 0 up to n minus 1. So when n is equal to 0, every series starts with the term 0. Every series starts with the term 0 because you start with an empty sum. The algebra should be the same algebra regardless, but we do have to get the right answer. And we have to get the indexing right. Okay, let's just do it together. Bn. So now we're changing the 2's to 1's. So 1 minus 1 over n plus 1. That's the induction hypothesis. An, well, we can use the original version or we can use the fancier version. I mean, if we use the fancier version, then we're basically done already. Because these two terms cancel. Okay, so actually it must have been 1 over n plus 1. That has to be the answer for Bn, because otherwise this algebra wouldn't have worked out.
Wait, so
Brandon.
in the base case of n equals 0.
Yes.
0 is not going to be the a of 0.
Well, it is. It's not a of 0. It's b0 is equal to 0. And 1 minus 1 over 0 plus 1 is actually 0. So even the base case is okay. Just not, it's not equal to a0. Yes. An empty sum is defined to be 0. An empty product is defined to be 1.
So based on this framework, like every single series you could ever imagine always starts with this.
Correct. Anything that's a series starts with 0. And then you add the first term of the sequence, you add the next term of the sequence, and so on. Let's do it. Should we prove this formally before we do it in the game, or you kind of see what we're going to do? Oh, what is the game? The game, the first level of the game is simply asking you to prove exactly this formula. For all n, sum in the range of n of ak, the sequence sums to 1 minus 1 over n plus 1. So the game knew the right answer, even if we didn't right away. Shall we do it? Okay, step 1. Intro, give me the little n. Intro little n. Now what are we going to do? Induction. Prime n with nhn. 2 goals. One goal is an empty sum, and over here is a number. I don't know, bound, please. Great, bound took care of it for us. How about the other goal? So now we know that the sum up to k is this, and we want to know that the sum up to n plus 1 is that. What should we rewrite? Sum range successor, exactly. Rewrite sum range successor. Again, I'm doing this naked for time. Okay, so we have a sum over here, and then the an. Now what? What is it, Damien? Yeah, you said it. Rewrite the induction hypothesis. Oh, and a of n. We need to rewrite both of them. Yeah, exactly. Rewrite, let's stick in the induction hypothesis, and let's stick in HA specialized, although you don't have to specialize, Lean will figure it out, to what? N. When I rewrite those two things, I get this mess. And now what do I do with this mess? Ring won't do it because it's not ring operations. First, field simp, let's cross multiply everything. And field simp will know that when we add 1 to natural numbers, now are we going to have problems with ring? We're going to have one problem with ring. One very annoying problem with ring, which is that first we add n plus 1, and then we cast it up to the reals. So first, let's push cast to get rid of that. And should we try ring and see it fail? And so this is like, you know, oh, well, it didn't finish it, so it failed because that's not what we wanted to do. But if we push cast first, then I think ring should close the goal. Okay, so that's one thing to be careful of in the game. All right, next. We just proved that the partial sums of this Leibniz series look like 1 minus 1 over n plus 1. So prove to me that the series converges. This should be very simple. What is the meaning of series converges? Partial sums converge. And what does it mean for the partial sums to converge? Iman? Yes. First, I need converges means There exists an L. So what's the limit? 1. So what's the first thing I should write? Use 1. Okay, use 1. So use 1 says, okay, and of course, Lean could see through the definitions. Use 1 says, seek lim series of A 1. Why does the series of A converge to 1? Because we just did it. We have to put something in here. What's a good, did we give that a name? We must have given it a name. What was our new theorem called? Was it called Leibniz? Yeah, Leibniz series prime. Leibniz series prime is that this sum is equal to 1 minus 1 over n plus 1. Well, is there a slicker way to do this than going into the proof? You can probably do this with the algebraic limit theorem, but it might be a little tricky to get all the you need to set up maps from n to the sum of things. Let's just do it directly. Let's do it all together directly in one fell swoop. So what's something that you can do for this seek lim? What was the first step if we're going to do it directly? Intro epsilon, yeah. Give me the epsilon and the fact that it's positive. Okay. And now, how large should I take capital N? Other than Suhas. What will this difference be? We know that the series adds up to
1 over n plus 1.
yeah, 1 minus 1 over n plus 1. Subtract 1 off of that. This is going to be 1 over n plus 1. How do I make 1 over n plus 1 less than epsilon? Arch prop. Okay, so let's choose NHN using arch prop. Now, do we care that it's n versus n plus 1? Actually, n plus 1 makes it even better. All right, so we've got an n, and the fact that n is less than 1 over epsilon. So what? Use n. That's the n that we want. Use n. Intro NHN. Okay. Now let's rewrite. I wonder if we can rewrite directly. Let's try rewriting Leibniz series. So rewrite. This is going to be a real test of Lean. Okay, you ready? I think that it should be able to go into here, find this expression inside the definitions, figure out A, but it's not going to figure out HA. It's not going to figure out HA. So we better give it A and HA. The A it'll figure out because it's an object, but the HA it's not going to figure out by itself. Fine. So if we feed it A and HA, and again, we shouldn't have to feed it the A. It should figure out what the A is. That's called Leibniz series. Leibniz series prime should have A in curly brackets so that I don't have to give it the A, but I do have to give it the HA. Let's see. No. It could not find a summation of AK up to N because it didn't know what N was. If I give it the N? If I give it the N, will you find it? Still no. It couldn't find this expression inside this expression, even though that's the definition. Sometimes it sees through the definitions, sometimes not. Okay, so we have to change first. Let's change the goal to sum K in range N, AK minus 1 is less than epsilon at the goal. And now I should have copied and pasted that rewrite so I don't have to write it out again. Leibniz series prime, AHA. And now I don't think I have to give it the N, it'll figure it out. Okay, good. All right, I'm going to cheat and hit this with ring. And now I actually don't like what ring did. Well, maybe it'll be okay. Maybe it'll be okay. Will abs neg do it? I think abs neg will do it. Let's see. Rewrite abs neg. Good. And how about rewrite abs of non-neg? Abs of non-neg to get rid of the absolute values. Beautiful. Again, I'm completely breaking all of my own rules. You know, I want you guys to say what you're doing rather than just calling these commands. Thank you. So it figured out, it automatically under the hood, miraculously, managed to figure out that n+1 is positive. So its inverse, well, actually, at least it's non-negative, and so its inverse is non-negative. And it managed to get rid of the absolute values for us. Okay, and now why is that true? Well, we probably have to do some cross multiplying. Should we do it? This won't be that hard. Let's try it a really fast way. Let's try field simping. Field simp, both at the goal and at HN. Let's cross multiply both of those. We cross multiplied that, we cross multiplied that. Let's lift HN. So have HN prime. This is the part that really needs to be better by exact mod cast. So I'm lifting this to the real numbers, HN. Okay. And now bound probably won't do it because bound is very stupid. I'm sorry, bound. I didn't mean that. I take it back. Bound is the greatest. N times epsilon is less than or equal to n times little n. I think bound will do this for us. Failed. Really? Oh, thank you. I guess there's a good reason for bound to have failed. Won't let you do typos. Now it's succeeded. Beautiful. And I think this together, what just happened? I think this together with, so this is just adding an epsilon to n times epsilon. And I already know that n times epsilon is bigger than 1. So I think just linearith. What do I have to feed it? Hn double prime, H capital N. Couldn't do it. Really? Oh, and that epsilon's positive. Is that what you're going to propose, Jeffrey? Reload. There's a bad linearith followed by a good linearith. Go back to this version and something's funky. Ah, very good. It did. I missed that. Very good. Let's go back. Let's go back. Where did it? Right here at spike gold 2. Okay. So abs neg, in fact, did not succeed in proving the positivity. It left the positivity as a secondary goal, and I missed it. Okay, so abs neg left this positivity as a secondary goal, which now we're staring at. And come on, bound. Do your thing. What? No. Because I'm still here. This is what I get for, oh my God, what just happened? I lost everything, didn't I? Rewrite abs of non-neg. And then what did we do? We field simped at the goal and at HN. And then we had lifting from the natural. Okay, we don't need to do this, right? You guys, I'm just going to go on to the next level. Next. Okay. Series order theorem. Let's prove the series order theorem. Let's look at it here. So if AN is at most BN, why is the series of AN at most the series of BN? I think, yeah, we could just do this directly, right? We don't need to talk about it in natural language. This is obvious, maybe. Intro N, give me the N. Induction and induction prime N with NHN. Beautiful. We need the case N equals 0. Why is that inequality true? Well, bound will do it because bound knows that each of those series is 0. Every series starts at 0. So bound did that. How about this one? it would be some range suck, but I won't see it, unfortunately. So we have to change to what? Some k in range n, a k, and this is not n, but n plus 1, is less than or equal to the same thing with b. Okay? So far, so good. And now we should be able to rewrite, again, I'm cheating, some range suck, and we can do it again. We could have done both in one fell swoop, but I did it once for AN. I'm going to do it a second time for the BN. Now the BNs have been summed out. And should I make the same change at HN? Actually, I'm going to do something better. I'm going to change this back to series. Change series AN plus whatever. Oh, this is a little slick thing. You can put underscores and it'll try to find the pattern. And if it finds the pattern, then it'll let you do it. So you don't have to write out something long. Okay.
One doesn't work.
And now this is good. We just have to specialize HAB to N. Specialize HAB to N. And Linerith. Linerith with HN and HAB. Done. Okay. Very good. Let's prove let's solve, well, not solve the Basel problem, but at least show that the Basel problem might have a solution. So what's the Basel problem? Let's talk about this in natural language. So here's another sequence. The sequence is a quarter, a ninth, a 16th, a 25th, 136th, 149th. What is this sequence? The reciprocals of n squared. Okay, the reciprocals of n squared. So AN is what? 1 over, but it starts indexing at 0. This is 1 over n plus 2 squared. Okay. What does this sum up to? Very, very good, and very close, not quite. So you've seen this sequence before. What this sums up to was a great mystery for the Bernoulli brothers. So Jakob and Johann Bernoulli were mathematicians. Did we talk about the history of this stuff a little bit, right? 1660s is when like Newton figures out lots and lots of calculus. We should go back to the 1400s where we have Madhava. We should go back to -300 where we have Archimedes and lots of people in between. I mean, we talked about, I think on lecture 1, we spent some time talking about this stuff. Maybe I'll call it 1670, you get Leibniz. Leibniz has read Newton's works on this topic, but says he understood nothing and just independently invented calculus. Newton doesn't tell anyone about did anybody take AP fluxions? Nobody took AP fluxions. That's what Newton called it. The theory of fluctuations, instead of derivatives and calculus. But Leibniz wrote a thing on the calculation of a bunch of things, which became calculus. He taught calculus. So Newton, didn't really, no one could understand what he was doing, and he didn't teach anybody, but he was doing all these amazing things. Much later, he came out with the Principia. The Principia is, Newton's laws of motion and all the physics that you hopefully have heard of. Leibniz starts teaching calculus to the Bernoullis. Bernoulli, Jakob and Johann Bernoulli. There's a whole family of Bernoullis. There's like 16 of them. And Johann Bernoulli starts teaching calculus to this young 12-year-old, maybe teenager named Euler, Leonhard Euler. Okay, so this is like, so now we're up to, I don't know, 1720 or something. I'm just making up some numbers. So the Bernoullis learned calculus from Leibniz when they were already adults. Euler was the first calculus native. He spoke fluent calculus. He was born with calculus in his blood. Okay, and that's what, that and the fact that there was so much low-hanging fruit when you're the first to stumble onto a massive continent and you start going around and there's gold here, there's gold here, there's gold everywhere, right? So that's the 1,000 papers of Euler who dominated the 18th century. But the Bernoullis became very, very interested in this series. They knew that it converged. That's going to be my question for you. How did they know that it converged? But given that it converged, it's not going to be hard to prove that it converges. It's going to be much harder to figure out what it converges to. So you could try to do the same thing. What's a quarter plus a ninth? Good. Yeah, 1336. And if I add, so 1336 plus a 16th, already it's no longer pleasant to work it out. What is it?
61.
Over 144, okay. And then how about if I add a 1 to 125? I'm just gonna go until Jeffrey's had enough. Right? So it gets nasty. And then you start working out what it is, and it's like, the way I've set it up is, I don't know, this is what is this? It's about a third, right? 0.3 or something. And this is maybe 0.32. You start working out some decimals, like it just doesn't make any sense. They could not make heads or tails of it. And they were in Switzerland, in Basel, Switzerland, and this became known as the Basel problem. The Basel problem. What is this sum, this series? Yes?
I just wondering, like, the timeline, were they familiar that pi just shows up in random places?
No. No, they were not. It showed up in, no, because the other places where it shows up are much later. Like I'm like, oh, it's all everywhere in Gauss, the Gaussian distribution. Why is pi in the Gaussian distribution? What does flipping a coin have to do with a circle? There's a long series of places where pi shows up unexpectedly. The vast majority of them happen after this. So it was a complete shock. By the way, Euler couldn't get a job. He was dying to stay in Basel, in Switzerland. He's this young guy, brilliant guy, doing all kinds of things, winning prizes. There's a bad job market, and he had to ship out to anybody know where he really started his career? St. Petersburg, exactly right. He shipped out to Russia because that's who was hiring. Okay, so he gets a job out in Russia, and there he, breaks this problem wide open and 1,000 other things, and eventually is recognized. But he really struggled early on, despite his brilliance and later great success. So he figures out what the series is. Roger is going to give it away for us. Tell us what it is. You were almost right. The series is pi squared over 6. Had I started the right way, which would be to start with a 1/1. But because I didn't start with a 1/1, it's pi squared over 6 minus 1, which maybe would have been slightly harder for Euler to find had he not started it the right way. Where you start sometimes matters. You'll see in a second why I'm not starting with 1/1. So the goal of this little exercise is simply to show that there is a problem. Because if this series diverges, then there's nothing to do. There is no limit. So our goal is to show that this series 1/n+2 squared converges. We're not going to be able to do it yet by saying, here's what it converges to. So how are we going to get it to converge? Roger, you got an idea? Yes?
It's less than 1/n+1 and n+. The sum of.
It's certainly less than something. It's less than something that we have just played with. Exactly. It's less than the Leibniz series. I'm just going to make, instead of an n+2, I'm going to make one of those terms one smaller, which will make the reciprocal one, a little bit larger. And this series we know converges. That's why we prove the order theorem. Okay? So we have that the series is bounded. Because, so again, we're just sketching. The idea is that the series 1 over n plus 2 squared, which is why I didn't start with 1, so that I could say it like this. This is bounded by the series n plus 1, n plus 2, which we know what that sums up to. We just did it. 1, that sums to 1. Okay, the series is bounded. The sequence of partial quotients is bounded. How does that get us that it converges? Suhas.
I think it's, series monotone.
It's monotone. And so there are two ingredients. So ingredient 1 is it's bounded. The series, the sequence of partial sums, is bounded. And 2, the sequence of partial sums is monotone. And what do we know about bounded monotone sequences? They converge. Okay? So that's how we're going to get that, Akil. That's right. I think that's one of your upcoming homework problems. Okay? Is to just generalize this. We're doing it from a historical perspective. Here's what actually happened, how people were playing with these things. But now let's do it, properly. I mean, it's slightly ahistorical because we're doing it rigorously. The people that were doing this were just doing it. It was sufficiently rigorous for their day, but no longer rigorous for where we want to go with it. Okay, very good. So let's have a look. We have a new theorem. The new theorem is called sec conv of monotone bounded. So what we had already is Cauchy of monotone bounded. And then there's another theorem that we had, and I'm just stapling those two together so we don't have to go through is Cauchy and converges of Cauchy straight to the sequence converges if it's monotone and bounded. Okay, so if you click on that the name of that theorem, it says you have a sequence, you have an M, you have that the M is an upper bound for the ANs, and you have that the sequence is monotone, then it converges. All right, well, let's apply this theorem. We're trying to say series converges, which means I think if we apply, it should see through the definitions. Want to try it? So let's apply a sequence converges of monotone bounded. We're going to have 3 goals. The 3 goals are, first of all, that the series is bounded by something. I don't know what that thing is. Actually, this is maybe not I should probably, then we're going to prove that it's monotone, and then goal 3 is give me the number. So actually, I think I should specify what the number is. So let's retry this so that we don't have to do something weird. What's the sequence? Series of A is the sequence. What upper bound are we going to give? 1. The partial quotients will all be bounded by 1. And then let's just send that. So we will have to prove that the partial quotients are indeed bounded by 1 and that the partial quotients are monotone. Good. Now there's only 2 goals. The first goal is for all n, the series is bounded by 1. The second goal is that the series is monotone. All right. So how do we work on goal 1? Intro n. Give me the n. All right. The series of the ANs are bounded by 1. Jeffrey. Oh, go ahead. Go ahead, John.
So when we talk about how
Yes. Exactly. So what was the Leibniz series? I'll call this lie or something. for all n, well, let's just call it, let's make a new sequence called Bn. Let B be a sequence sending n to n that's a function taking n. Do you know the slick way of doing this? You can just say let Bn colon equals 1 over, let me make sure it knows it's a real number, and then it's n plus 1 times n plus 2. Okay, so we have B, and whenever you let something, what's a good thing to do? Let's do a half, a stupid half that records what it is. HB says for all n, Bn is equal to 1 over n plus 1 times n plus 2. What's the proof? Intro n, refl. Perfect. Okay, so we know what the Bn's are, and now what was that called? It's called Leibniz series prime or something. Leibniz series prime. Leibniz series prime is that if you have a sequence that satisfies what we just said B satisfies, then its series is equal to 1 minus that. So I wonder if I'll be able to do that directly. Probably not. I'll probably have to do a change. Okay, so let's have B series says for all n, sum as k ranges in n, bk is equal to 1 minus 1 over n plus 1. This is by applying Leibniz series prime to the sequence B, the fact that B is equal to what it is, and the number n. Oh, I have to intro n first, of course. Intro n, and then apply this with n. What's the matter? Oh, okay. I tried to be a little too slick. And I didn't specify the type of n. And therefore, it guessed that because the left-hand side is reals, the right-hand side, the input should also be reals. So that's why it's not working. Let's see if we can fix it by being more proper here. It's a function from the naturals to the reals. It's a function that maps n, to that. And now hopefully everything works. Now everything works. Let's try that. Okay. So we know that for all n, this series is equal to 1 minus whatever. Let's specialize this B here to n, because we have an n. We're going to compare that to an. Let's specialize B series to n. Does that make sense? And now what do I have to do to, let's change this. Let's change at B seer to say series Bn is equal to 1 minus 1 over n plus 1. Okay, great. Now it looks a little nicer. And now what's the last thing I want to say? Say it again. I have to say two things. Which two things? Exactly. I need to say that A of n is less than or equal to B of n.
Series B
And then the order limit. Because the ANs are bounded by the BNs, we'll get that the series of the ANs is bounded by the series of the BNs. And then we can chain those two together. Okay, so let's have HAB is that for all n, AN is less than or equal to BN by intro n. And then what? Bound won't do it until we field simp. Can we cross multiply? Or maybe, maybe we should rewrite the HAB and so rewrite HA at n and HB at n. Actually, n is a bad dummy variable. Well, yeah, it is a bad dummy variable because we already have an n floating around. So I don't want it to get confused about which one is which. It probably won't, but just in case. Okay, and then I think if we field simp and then bound, that should do it. Okay, so we know that we know that we have this inequality. Then we had the order. What was it called? There's a goal too. Yeah, that's the monotonicity. We still have to prove the monotonicity. That's correct. Where's our series order theorem? The series order theorem. So what does the series order theorem say? It says if you can prove that an is less than bn, then the series of an is less than the series of bn. Perfect. So have H here is that series an is less than or equal to series bn by apply series order theorem to the sequence A, the sequence B. Again, I shouldn't have to give those. I could put those in curly brackets. How do I know that an is always less than or equal to bn? HAB. And what value of n? N. Beautiful. And now we're done. I think we're done. Is Linerith going to give me trouble with 1 over n plus 1 being positive? Just in case. Just, yeah. This is we'll call Hn, which is that the real value of 1 over n plus 1 is non-negative by bound. Okay, and now Linerith with Hn, H series, and B series should do it. Let's see. The series of An by H series is bounded by the series of Bn. The series of Bn by B series is equal to 1 minus 1 over n plus 1, and 1 over n plus 1 is positive, so that subtraction should be less than 1, and Linerith should put all that together. Okay, monotonicity. Why is the series monotone? Exactly.
So you could just do like the monotone successor thing.
Exactly. Yep, I don't either. It's probably called monotone suck or something. Monotone of suck. If you know the successor is monotone, then that's enough to. So let's apply monotone of successor. So all we need to know is that from n to n plus 1, we increase intro n. Give me that n. It's not going to see through the definition, so I guess we have to spell out the definition. Change sum k in range n. AK is less than or equal to sum k in range n plus 1 AK. Now what? Exactly. I'll rewrite sum range successor. That breaks up the end. Now those two things are obviously the same. How about why is an positive? Maybe specialize HA to n. And then, I don't know, rewrite. Yeah, let's rewrite by HA so we know what that was. And then let's have HN, which is that the real number 0 is less than or equal to 1 over n plus 2 squared. And I hope bound will do that for us. It does. And finally, Linerith, where the only thing we have to feed it is HN. That's the Basel problem. Okay. We actually got through a lecture for once. Let's look at problem set 16. Just to, this was just posted. I think some of these you guys could do formally if you really wanted to. But basically, the first problem is prove that the sequence, that the exponential sequence, x to the n, x is fixed, and it's a map that sends n to x to the n, where x is between 0 and 1, prove that that converges to 0. You can do it directly, of course. This is all in natural language. But there's a slicker way to do it. The first is to show that the sequence is antitone, decreasing. Why? Right? So you could do it antitone of the successor. And every time you're multiplying by something less than 1. Okay. Why is it bounded from below? Because it's non-negative. Yep. Bounded by 0. It's antitone and bounded from below. Therefore, it converges to some limit. Once I know that it has some limit, I can do all kinds of things. Here's another sequence. Well, instead of taking n to x to the n, I'll take n to the x to the 2n. That is merely a subsequence of the original, because 2n is an strictly increasing sequence. So if you have a convergent sequence, then the subsequence converges to the same limit. So x to the 2n converges to the same limit. On the other hand, x to the 2n is also x to the n times x to the n. And x to the n converges to L, and x to the n converges to L, so their product converges to L squared. And you should be able to finish the proof from there. I hope. On one hand, it converges to L. On the other hand, it converges to L squared. And there's only 2 values of L that satisfy that property, and it can't be one of them. You have to rule all that out. Then problem 2 is that I don't think I need to say anything about problem 2. I think you'll figure this one out. I probably don't have to say anything about problem 3 either. Do we want to talk about problem set 15 that you just handed in? Ayman,
I had a question about the problem set.
please.
The Cesaro average.
Yes.
Earlier did question was just that can it be defined when B is 0? Can it be defined for B 0 because then it divides by 0?
Yes, because division by 0 in lean is just 0. So
yeah,
B of 0 is just 0.
Weren't in this form, that's why.
Oh, no. It doesn't, the first term in the sequence isn't going to change anything. How'd you guys do Cesaro? That's a good one to go over in 3 minutes. What's that? There's only really one big idea. Akil? Yeah. Why, if AN converges to L, does Cesaro average Bn defined to be A0 up to a n minus 1 over n also converge to L? Okay, so go ahead, Akil. AK with a 1 over n, that's B of n.
Because A of n converges. It's like A of n converges, so you can break that sum up.
Right, you split it by like the n value that's given from the individual thing.
All the terms of n equal to that capital.
Yep. So the first thing is this is an average, so we can pull the subtraction up by L inside. And then this we can break up into the early terms and the late terms. The late terms are all bounded by epsilon over 2, say. So the late terms in this sum are bounded by epsilon over 2. The early terms in the sum, well, the AKs are bounded. So if the AKs, so if for all n, A, n is bounded by some capital M, it's a convergent sequence and hence bounded. So this term inside is bounded by M plus, let's say, absolute value of L. And then how many of them are there? There's only n1 of them, and n1 is fixed. And we're dividing by little n, but little n is going to infinity. So how do I get this? So if I can get the early terms to be at most epsilon over 2, and I get the late terms to be most epsilon over 2, then I sum the two and I get at most epsilon. So the way to get this thing is to make sure that n is sufficiently large, which is just by Archprop. Archimedean property where you divide by, once you fix the epsilon, you get the n1. Once you get the n1 and the bound, and the L, you can divide this stuff to the other side and make sure that n is greater than n2, where n2 is greater than what? N1 times M plus L, of course, there should be parentheses here, divided by 2 epsilon. And that'll get you the Cesaro. Okay, so you break it into early terms and late terms. The late terms have a good property. The early terms don't, but there's few of them. That's the kind of thing I want you guys to get really proficient with. Thank you.
So, demonstrate that you're splitting with someone.
That's what we're building up to. Yeah, we're gonna need to split sums up and do all kinds of good stuff. All right,